But yesterday we have started steady diffusion equation, and the equation which you have solved is, yeah, can you recollect? This is the equation. At the end you have solved for, isn't it? Separately we have solved the this term d by dx of k into dt by dx, where k is given as the thermal conductivity. Can you recollect? Is it okay? K is the thermal conductivity, and we have discretized that one, and we have written it as a this one tridiagonal form. We have chosen 5 nodes. Am I correct? We have chosen 5 nodes, and you have the code also, and that code can be increased for any number of nodes. So you have tried for 5 nodes, increase that to 10 nodes. That means you have to give delta x as proper one. Yesterday we have taken 0.1 delta x. Instead of that, yeah, that's it. Okay, 0.505. You have to take 0.05. Then automatically you will get that nodes, and you have to take care only the boundary nodes. Isn't it? Boundary nodes. Yeah. This one. Isn't it? This is the half boundary. This is one boundary, and here is one boundary. If you write down only separately for the left boundary and right boundary, it is enough. Okay. Now let us see how to deal with the nonlinear term. Yeah, this is the time discretization. Later we'll do. Now I want to show you for the, this one. Convection and diffusion equation. So now we are going to deal with this convection one. So here we are again going to take about this mass conservation equation also along with that. So what is the use of that one? If you recollect, already I showed you that we are calling this rho into u as flux term, F. Isn't it? F we are going to call this one. So integrating over the control volume. Integrating over the control volume from where to where? Yesterday also we seen, no? Here we have a control volume, and here is the point node P surrounded by the control volume. If we take the control volume, so varying from west to east. West to east. So the first equation, integral of one D case, no? So integrating from over the control volume. Okay. Then if I integrate this one, so what we are getting? Isn't it? Isn't it? Rho E at the upper one minus the lower. We write down this one, then we can write down this as the notation only. What happened? Huh? Rho U. Yeah, it's a velocity. At some phi also people used to denote whatever they want. Okay. Especially it is for velocity, so we are specifically writing. Yeah, correct. Yeah. What is F here? Flux term. Okay. The other one we have the diffusion term also. That is what it is written here. Okay. So we are writing this one as rho u5 minus, I think you can recognize the left side. Again we are integrating over the control volume. The second equation is written here. The second equation is integrated over the control volume from W to E. That is why we have here this term. Same thing only written here. Yesterday we have seen only the right hand side part. Now here we are having the left hand side part. Now what is our aim? How to find out this phi value in the left hand side. One way is phi E is located here at this point. Okay, so what we are doing? We are taking the average of the neighboring points. So instead of phi E, we are replacing that one with phi P plus phi E divided by 2. So what about this point? Phi W, it is the average of these 2 points. Okay, you see there. See here, it is the average of the neighboring points. Again here. Okay, so that is what it is written here. Now the notations are shown here. F and this diffusion, flux and diffusion. So one way to deal with this nonlinear term is rewriting like this. Now again you have to collect the usual way. AP phi P equals to, can you recollect? Yesterday we have written now AP TP equals to, now we are going to write down the next step. Instead of T we have here phi equals to AE T, phi, isn't it? Yeah, phi E plus AW phi W. For each node you have to write down, again you will get a system of tridiagonal equations. How to solve that one? There are many methods are there. Okay. Thomas algorithm is there. Not TDMA is there. You can solve that. Using that one you can solve. Otherwise, what else we know? Yeah, nowadays we are using this algebraic multigrid method also to solve the system of equations. Okay, let us move on. That is what it is shown here. So AE is this diffusion and flux term also. AW is diffusion at the nodal point W and flux at the nodal point W. And AP is the combination of AE and AW. I think you know this now. What is the value of this one? Here you see FE minus FW is 0 because we are using the mass conservation equation. So this term collapses. So we are left with this one. See, it is written as since by continuity equation this is equals to this one. We do not get the property of this one. We do get the property of this is a combination of this one. Always AP is a combination of this one and these terms should be positive. Okay. So now some examples are given. If this diffusion values are 1 and the flux values are 4, then what will happen here? So the neighboring nodes is this one. Phi value is 200. Right hand side value is 200. Left hand side value is 100. In between we are getting 50 only. Okay. So otherwise what is happening here? If these values are this, then there will be oscillations if we choose this type of linearization. What it is telling here is if phi is discretized with respect to the neighboring nodes like this, there exists some oscillations in the solutions. That is the idea behind this one. So how to overcome that one? How to overcome, you see, since in reality cannot fall outside the range of 100 to 200. Left side is 100, right side is 100, but we are going to get the value of 250. If you solve these equations, we will come to know this value. Okay. So we cannot have such type of unrealistic solutions. Hence, we are choosing another method called upwind method. Okay, I will show you here. Yeah, upwind scheme. The name itself tells that the movement will be in the upwind side. Okay, if it is in the downwind, choose the previous one. If it is in the forward side, choose the east one. If it is in the backward, choose the west one. Have you understood the idea behind that one? So we are not taking the average. We are going to choose the neighboring value according to the flow direction. Okay. According to the flow direction, we are going to choose that one. So that is what it is given. The value of phi e at an interface is equal to the value of phi at the grid point on the upwind side of the face. So here you can see very well that, okay, what is the value we want? We want to know the value of this one, phi e. So what it is given? If Fe is greater than 0, what is Fe here? This one. Fe is rho u e. If this value is greater than 0, then choose like this. In the code, you have to write down phi e equals to phi p. If Fe is greater than 0. Otherwise, you have to choose like this. Okay. The same value. Otherwise, you have to choose phi e. If it is less than 0. This value, what is this? The control phase value at E of the variable phi is greater than 0. Then choose the previous one. If it is less than 0, then choose the neighboring one at the point E. So this is the idea behind this one. So now we are rewriting that equations. Instead of u phi, we have written here rho u, we have written here f. Instead of rho u, we have written here f. Okay. So in a mathematical formulation, we have written this. Okay, this way. So it is evidence from the above equations that no negative coefficients would arise. Thus, the solutions will be always physically realistic. That means one solution is positive, immediately in the next neighboring point, the solution is negative. Like jumps will be there if we use the previous one, that is average of two neighboring points. Okay. Instead of that, if we use the upwind scheme, that condition will be avoided. Okay, that is the advantage of upwind scheme for the convection term. Yeah. So this is another scheme, exponential scheme. Even upwind scheme gives the better results in comparison with other schemes like exponential scheme. Another one is quick scheme we call quadratic, hybrid scheme. There are many schemes are there, exponential scheme and hybrid scheme. Then power law scheme, the quick scheme also there. If you go to this ANSYS software or COMSOL software, they will ask you how to deal the convection term, which type of method you require, whether you require upwind scheme or hybrid scheme or exponential scheme, etc. You have to tick there. Okay, but you should know the methodology behind that one, what is happening there. So now if time permits, we go to the lab later and we will do this upwind scheme problem. Okay, one problem we can try there. So that is what I want to say you. The next one is about the convection diffusion equation. Already we have seen for one-dimensional case. This is for two-dimensional case. That means we are going to consider y direction also, x and y together. Okay, in the figure it shows like this. So in the compact form, how we are writing the system of equations? Already we have written for this AE phi E we have written, AW phi W we have written. Now we have to include north and south also. If it is a 3D case, top and bottom they call. Instead of telling Z side, they used to use the terminology called top and bottom. Okay, I, J, K. In the x direction we use I, y direction J, the z direction K. Okay. Okay then. So all the coefficients are given here, including the source term. So this is what I want to stress for this 15 minutes about the how we are using the convection term, how we are dealing the convection term in the finite volume method. Okay, okay then. Stop. Yeah. So as a part of this GIAN course, let us welcome Professor Rameshwar from Osmania University, Department of Mathematics. He contributes a lot for such type of problems. Mainly he works in this plane layer problems. Okay, plane layer rotating magnetoconvection. Different types of problems he used to work from his PhD. So he uses analytical methods, not like me. I am using computational methods, but he uses analytical methods. Mostly they are called as weakly nonlinear analysis about the linear stability. Linear terms and then nonlinear terms also takes, and it has been expanded as a series form. Especially they are using the perturbation method. So we thought of introducing you the perturbation methods in the starting, then its applications to such type of problems. Okay, plane layer problems. Up to yesterday or here afterwards, we are going to see about the spherical convection, isn't it? Yesterday and all we have seen much about the spherical convection, but here we are going to see about the rectangular coordinates x, y, z. Okay, so I welcome Professor Rameshwar to deliver the lecture in this GIAN course. Okay then.
Okay. So thank you very much. So I'm audible to you all? Right. Okay. So good morning. And firstly, I'm thankful to the coordinator as well as Professor Sergey Starchenko and Professor Maria from Russia for coming over here. And really, we have very good time to have the discussion with the collaboration with these foreigners. So thank you very much. So as a part of this course, the chance was given to me to present work on these perturbation methods. Of course, we have two types of perturbation methods. So one is the regular perturbation methods, and other is the singular perturbation methods. So how to classify this? Sometimes I will take the help of this the pen. Okay, please try to see. And suppose that we're having say problems like regular perturbation. So methods. So another is, let us see, this is one, and next one is say singular. So perturbation. So methods. So we have that is we can say that is perturbation methods. Perturbation. So methods. Perturbation methods. So this is classified into two parts. One is the regular perturbation methods, and other is singular perturbation methods. Okay, singular perturbation methods. So here in this lecture, we try to cover about the regular perturbation methods. So when we call a model or a problem as the regular perturbable problem, and when we call a problem as the singular perturbable problem, it is like this. Suppose let us start with some algebraic equation. Say example we take, and suppose that we consider epsilon is a small parameter. Epsilon is a small parameter. If it is occur either in the algebraic equation or in the partial differential equation, maybe ordinary differential equation, maybe partial differential equation, maybe integral equations. Suppose if these equations include small parameter, small disturbances. So in such case, we'll get such type of the quantities, and then so we can have the examples for such the algebraic cases. Algebraic cases we can take as the same x squared plus x and plus epsilon equal to 0. This is one. Let us take this is one, and this is let us take another example. Epsilon x squared plus x plus 1 equal to 0. So we have two types of models are here. So algebraic equations. So they include a small parameter epsilon. So in the first example, so what you can observe that the epsilon is coming in the equation, which is free from the variable x, right? So in such case, we call that is example for the regular perturbation problem. All right. So next example, if we take that the small parameter epsilon, so that is coming as a quotient of highest power of the variable x. So in that case, we call this second example as the singular perturbation problem. Okay. So and similarly, we can take the examples. This is algebraic equations. So and other case we can have the differential equations. Say dx by say dt. Let us call and plus epsilon x is equal to 0. Homogeneous equation we can take homogeneous. Otherwise, we can have that is the case of non-homogeneous. Also, we can take in this format. Okay, maybe dependent variable, maybe dependent, and for example, independent can have. Okay. So in this example, what you can see that epsilon is a parameter, small parameter, and it is coming as a quotient of say dependent variable x, right? And of course, we can have that is another type of example. This say d square x by say dt square plus epsilon dx by dt and plus x is equal to say, for example, f is function of x comma t. If you take this, so in this example, if you see that the epsilon parameter is occurring, but it is the quotient of the next lowest power derivative terms, right? So hence these two examples we can take as a regular perturbed the models, right? So similarly, let us go to the next one. That is for the case of these singular perturbable problems. Say for example, if we call this epsilon is occurs as a quotient of such case, right? So and other one, let us see that is epsilon d square x by say dt square and plus say dx by dt and plus x is equal to say f is function of x comma t. Suppose, so here in the second example you can see differential equation. Epsilon is a parameter occurring as a quotient of highest derivative of the equation, right? So in the case of algebraic models or in the case of the calculus differential equations, the idea is the same. What is the idea? If a small parameter occurs say at any one of the stage, for example here or here, but free from this highest degree quotient, and here also you can see that it is coming here but is not connected to here. Okay, so in such cases this model and algebraic model, otherwise you take the differential equation model, in both the cases what happens, we can treat these models as your regular perturbable problems, right? Similarly, if you go to the next case, that is this model is what algebraic case. Here is epsilon is a parameter connected to highest power of x, and here also you can see that epsilon is a parameter connected to highest that is order derivative, right, of the equation here and here. So these two, we can say that this one are the examples for the singular perturbation problems, right? So in this way, we try to classify the regular perturbation problems as well as singular perturbation problems. Okay. So what are the uses? Of these models? Means of course, let us see small example. Say a physical example. Let us call this is the same. This is same. This is say simple pendulum. Let us take simple example. And then suppose if you introduce the small at t equal to t naught, assume that it is at rest. Okay, let us suppose. Okay. And then we want to understand the motion of this object. Suppose if we introduce small disturbances, right? Then whether the pendulum approaches to its original position as time keep on increases. Otherwise, it may change its position. So what is the motion? What is motion means what? It includes velocity and amplitude and periodic nature and frequency, etc. These all the quantities we can trace out. Okay. So for this model, for this physical model, we can take as for example, if you call this is a displacement, and assume that displacement we measure with the help of say theta, right? So we can have the measures like say suppose if any object is moving from here, this is x direction, from here to here, we take the displacement from say for example this is a position x0 to x1. So in this way we can have the displacement, the classification. And similarly, suppose that if any object is moving, the displacement we can express with the help of angle also. With the help of angle also we can discuss the displacement. Okay. So to understand the motion of this physical model, then we have that equation theta double dot and plus omega, and let us call say sin theta. We can say that this is equal to 0. So this is the equation. Will help us to understand what is the dynamics of this pendulum, that experiment. Okay, what is theta here? Displacement. So double dot denotes here what? Derivative of theta with respect to time twice. So you know that. So theta double dot, that is theta dot means what? Theta dot will give you the velocity. Do you agree or not? Theta dot is gives to velocity. Means what? D theta by dt we having. This is gives to velocity, And suppose that if you have double dot, so then d square theta by dt square, this will give you acceleration. Of course, this omega, so we can call this omega, we can take as say gravity divided by L, we can take, and L is what? L is the length of this, that is rope, or we can say string, one of the case. So in this way, we try to take this model. Of course, we have a lot of ways to derive this equation using calculus variations. We have like Hamiltonian, we can use Hamiltonian, Lagrangian. So these methodologies, we can use it to trace out this equation with the help of what? Kinetic energy and potential energy. If you know these two things, Hamiltonian we can find out, and accordingly this equation we can trace out. Okay, but how to solve this equation? That is the question. So we have framed the equation, very nice, but we have to solve this equation. So to solve this equation, what happens? Suppose that if you feel that okay, that displacement is very small. It means what? We can, if you say that is say sin theta, if you are having, this is very small. If you are having, say for example, sin theta by theta is very small. So mod sin theta is less than theta. So in such case, this sin theta will be approximated by with help of your theta, right? So in that case, you have this equation gets modified, and let us call this omega we having here, and theta is there. So this is the equation. This is the equation. Now this is a linear equation and homogeneous equation, and one can solve by using our usual methods, right? And also we have this is a chance to solve this model using your perturbation methods. Okay. So let us come to this point. So this is one of the applications. So if you open this mechanics books, we have a lot of applications you can find out. For example, suppose you're having that pulley is there, and then a mass, suppose that if it is moves in this direction m1, and this another mass we are having, this is in this direction m2, and then what happens for this is pulley, what happens, it is try to move this side or this side, and for this configuration, and from here to here L1 L2, and we can have that is a dynamical equation, and we can find out the differential equation. And of course, in general, these equations are nonlinear differential equations, right? And as you know that solving these nonlinear equations, we having some methodologies can give the closed form solutions, but not all. So then how to proceed for that? So suppose if the equation includes a small parameter, for example, say epsilon, and in that case, either you have the choice that use the regular perturbation methods or singular perturbations accordingly. So this happens in the solid mechanics. Like that, you can have many examples. And similarly, we can also take the if you solve the problems like fluid dynamics problems, right? So if you want to solve the fluid dynamics problems, you need some equations. What are the equations required? You're all fluid mechanics people, I hope. Can you tell me? Nernst's equation, one of the equation will help you to understand the velocity, momentum, velocity, pressure, and suppose if permits the temperature, for example, if it includes the buoyancy induced and temperature, etc., we can have it. And of course, this Nernst's equation is a vector equation, but if you convert it to the dimensions, 3 dimensions or 2 dimensions, accordingly number of unknowns will increase. So to trace out to get the solutions, we take the help of, for example, equation of continuity we take, right? That is one of the equation required. So with the help of that, so we have a lot of problems available in fluid dynamics like Poisson flows, plain Poisson flow, plain Cody flow, and Poisson flow and Cody flow. These combinations you can have, and one can solve the problems using your the methodologies given. Closed form solutions we can get, but if it is includes the small parameters, for example, Reynolds number you have, right? So if Reynolds number is very large, so 1 by R is very small, and if that is the type of terms included, then how to solve those equations? So for that, what happens, we take the help of the perturbation method to get it. Of course, so we have that is the lot of methods are there like approximate methods. What kind of approximate method you know? Numerical methods, for example. Numerical methods. Maybe, of course, finite difference method, finite element methods, finite volume methods, spectral methods, etc. All these methods we call as the numerical methods, which does not give the exact solutions. They give the approximate solutions. So similarly, perturbation methods also deals with the approximate solutions. That will not give the that is what exact solutions, right? So here is, of course, this is the equation you are having. This is the equation, and you can solve this equation as your quadratic methodology. You know, quadratic form like x squared plus px plus c equal to 0 equal to, how to find this is x value here? Minus b plus or minus b square minus 4ac divided by 2a. Use this formula and you can get the result, right? This is a closed form solution. And also, right? So what are the results you get from this? And using some ad hoc approximation. It is called asymptotic approximation, as we call it. What is that? Ad hoc. It means empirical it is. We feel that, okay, if you take this expansion, you may get a solution. Or if you take this way, you may get a solution. With respect to the small parameter existing in the equation. So then, like a power series, right? You know power series methodology, differential equation you have, and power series method is there. And expand, that is the solution in powers of x, for example. X is an independent variable. And then try to get the what are the constants getting in the power series, and finally you get the solutions, right? That is power series method. So here also we try to expand, that is in power series method up to some extent. And then what are the results you get, and both can be comparable. So what is that here is ad hoc basis. Ad hoc basis means what? That is called asymptotic method we can call. What is that? Asymptotic method. So those who are working in the perturbation methods, so they have to use this the terminology like asymptotic methods, right? Okay, so this is the small ideas about the applications of perturbation methods like mechanics to solve the problems of mechanics, which are obtained from this Hamiltonian's principle, otherwise by using your Lagrangian principle and by using your D'Alembert's. Do you aware of that? D'Alembert's principle, etc. Use these methodologies to get the equations of the dynamical systems to trace out this. Okay, that is one point. Solid mechanics it is. Okay, and similarly, fluid mechanics problems are there. So those problems are very dangerous, as Professor Rani said, that we get the problems of nonlinearity, right? And they are taking some help of this converter upwind scheme, forward, backward, etc. All the combinations, and they may give sometimes good results, sometimes they may not. We don't know. But of course, the perturbation method is also existing. If you use it, definitely you get the better solutions. Better solutions, of course. Right. So let me go into the small ideology. Okay. So now here I denote here. So most of the physical models facing by the physicists, engineers, and applied mathematicians to exhibit certain essential features. What is that? To exhibit certain essential features that exclude exact and analytical solutions, right? So it means what are the problems generally? So if you solve the problems like related to the fluid mechanics or civil engineering or chemical engineering, etc. So those models are nonlinear models, right? They are not linear. You know that how to classify the linear nonlinearity that is available with the help of some parameters existing like Reynolds number and so on. With the help of that, we can trace out laminar flows or turbulent flows and so on. And then, and suppose that structural engineering, for example, mechanical people, right, the designing, etc. So those are nonlinear. So it means what? The physical models confined into the real world. They are not linear models. They are always nonlinear models, right? So then what happens for the nonlinear models? We don't have closed form solution. We don't have methodology, right? If you Christians develop one methodology, okay, that is good, but we don't have that knowledge. At present, we are at this stage that is what are the available methods are there, just we had to use it. We had to use it and then try to implement to get the solutions. So this is only we have in front of us, but nobody have the time to develop some new method and etc. Right? So let us see. This is the problems we have in the first one. Okay, the features include nonlinear governing equations. That is what I was telling you. That nonlinear governing equations and nonlinear boundary conditions. Yeah, it is very important. Boundary conditions at known are in some cases unknown boundaries, so variable quotients or complex boundaries. Yes. So it means what? The important thing is you have use a mathematician, for example. Okay, you see that that the physical model is you have seen differential equations, and you feel comfortable. I can solve this. I have some method tools. I have with the help of the right to solve. But in that models, very important thing is that the boundary conditions. Boundary conditions. If you are able to give correct boundary conditions, then 90% the work done for the model, 90%, right? And suppose that if it is for 10% only you have to do, 10% you have to do with the help of your computer knowledge and using the softwares and etc. Only 10%. Whatever you are saying that I am writing this code and this is the problem I am getting, that is problem, that is only just 10%. But 90% is what? Fixing the boundary conditions. Correct boundary conditions, that is really challenging. It is not easy. Okay. The model and as also the boundary conditions. This together very important to understand about any physical configuration. Okay. Maybe in fluid dynamics or solid mechanics and etc. Okay. So as we know that, of course, if the boundaries are slab geometry, for example, okay, the matter is very simple. But suppose that if your configuration is like a zigzag, right? So in such case, the boundaries are very, very dangerous here, very complex boundary, and then to impose boundary conditions on that, it is not easy. Suppose that if you have slab geometry, so this is slab geometry, and this is horizontal geometry, this is x direction, let us suppose y direction, and the fluid is flowing in this direction. Suppose that this is fixed, this is fixed. Okay, it is fixed, and assume that velocity along this direction is moving. On the boundary, no slip condition. Okay, no slip condition is 0. Okay, and suppose that if you take that is on this boundary, suppose that if it is a free slip is there, and then what happens, we having that is u is equal to u, w we can take free slip. So we have shear stresses existing, and accordingly, and we can have the boundary conditions and we can work. But if that is like a complex geometry, okay, and you want to understand that is flow inside of this is the flow you want to understand, and due to this shape of the boundaries, so it is very difficult to apply the trace out the boundary conditions to get it. Of course, we have some softwares are the ready-made softwares like ANSYS and console and etc. So those softwares will take care of all these things and can give the solutions. Okay, that is what we have this point, the second para. So next is another one. Hence, the physicists, engineers, and applied mathematicians are forced to determine the approximate solutions using approximation methods. You see that. So we don't have any chance. We don't have any choice because the problems are very complicated. Nonlinear problems are there, so we don't have solution. Then we are forced. I think that all of you using that is closed form solutions are using our numerical methods. I am asking a question, that is you are solving the physical models, right? Then are you using the closed form solutions? Otherwise, you are using numerical methods. What kind of methodology you are using to solve the problems? Ritika? Numerical. Krishna? Closed form. What about you? Numerical. You? Analytical. Okay. What type of analytical method? Energy method. Okay. You? Numerical. Of course. So these methods, of course, I told you already. That is the numerical methods or perturbation methods are approximate methods, right? Not exact methods, right? So then, due to all the problems, all the people sitting here, so you are using that is approximate methods, either numerical, otherwise your perturbation method. Anyone you have to say, okay? Right. So this is what is the problem we are having. So the approximation methods may be purely numerical. What is that? Approximation methods may be purely numerical or purely analytical. What is the name? Naveen. So Naveen, you are using that is purely analytical, right? Energy method. And numerical, Ritika, you are using purely numerical, right? Krishnendu, you are using purely analytical, right? Okay. So this type of things we are having in the case of this analytical, that is approximation methods. Okay. So analytical, last one. The analytical approximation methods can be broadly divided into the rational and irrational. So that's what we have, rational and irrational here. So rational approximation method means what? In which I told you that is what are the expansion you take. That is just a ad hoc basis, right? You feel that okay, this is a way if you proceed, you may get it, and that is such type of expansion also known as asymptotic expansion. Of course, Krishnendu, you are taking that is expansions. Whatever you are taking, that u is equal to epsilon u naught plus epsilon u and so on. That's what you are taking. So that is nothing but asymptotic expansion we call it. Otherwise, other. Who told you to take like that? Right? Evaluate here. No. So it is the way we take, and suppose we submit it to the equation. Whether we get the solution comfortably, okay, this method is okay, and otherwise not. It is like a triangle. So hence it is called as ad hoc basis. Okay. And next thing is we have, okay, let us see about the perturbation equations are there. So when we call an equation, it's a perturbed equation. I told you already the definition is given here. That is either algebraic equation, otherwise differential equation. or integral differential equation includes small parameter, right? So in such case, such kind of models are that is known as your perturbable equations, and accordingly the boundary conditions also that is given, which may include the epsilon parameter. Okay. And what is x here? So of course x is a variable, we can have independent variable, we can have that, and epsilon is a perturbable parameter, and we have this. Okay, so this is one of the example, classical example, we can say the relevant convection to understand the pattern formations. You see that to understand the pattern formations, how many people know the relevant model? Right, you and Christian, etc. Okay, people you mostly know that relevant model that states that is take the fluid between two horizontal plates which are fixed, and then supply the temperature from below and observe that for what temperature gradient you get the motion in the system. That is what our motto, right? So of course you know that is Bernard, he was explained that okay, if the temperature gradient exceeds some critical temperature gradient, then we get the motion in the system. Maybe that is in the form of the rules. Depends upon the boundary conditions. Boundaries, maybe boundaries, if it is the perfect conductors, okay, rolls or hexagons are preferred near the onset of the convection. This type of analysis is given, and theoretically that problem was solved by Raleigh. So that is happened in 1916, and then he theoretically predicted that is okay. He would take the help of the Rayleigh number, and which obtained using proper scaling, which is very important. Which it is comes in the dynamical similarity. And with the help of that parameter, he said that okay, if that parameter exceeds some critical parameter, you are going to get this type of instability in the system. So to solve this model, so they have taken the help of the perturbations, because initially when you supply temperature to lower plate, you don't get convection at all initially. Do you observe or not? You put some water on the in a vessel on the stove and apply the temperature to that. Immediately, do you get the temperature to the top? No. You take some time. So initially it is stable state, it is okay. After some time only you feel that there is some warmness on the top. What is happening here? Here happening that is heat is that is heating the lower layer, and next to the upper layer, next adjacent layer, and keep on. So like that, it's continuous process. The heat is propagating one layer to other layer, and so on. It is approaches to the top level, right? So it is at rest initially. It is we call as a conduction state. So then next state is what? Small bubbles we find on the bottom. So it means what? There are some small disturbances occurring. So we call them as small perturbations. So how to understand the small perturbations? Let us take the help of the perturbation methods and to solve it. And happily, easily we can solve it. So initially in 1916, they have kept attention to solve this model using this analytical approach, right? Using closed form solutions. Okay. So conduction state we having it is we call as a rest state, and next state we have convection. It is known as the perturbable state we have. So we want to understand from the basic state to the next perturbable state. So what kind of the methodology we had to use to get the solutions, right? Right. So here is we are effectively successfully we have used the Rayleigh used the perturbation methods to get this the idea that how to explain for the occurrence of this pattern formations, right? It is happens in the fluid dynamics, right? Partially, it is like a partially type of flow. Okay. So then next we take this is you see this is small experiment. Of course, I took this is from the website, of course. So then heating it may be aluminum liquid, right, and heating from below, and then you can see the formation of this hexagon, right? So it means what it has six of course 6 sides. You take one step 6 sides and it's 6 sides, but of course all of them not 6 sides. So something having some defects. We are not interested about defects of if you can maintain the proper temperature gradient in the configuration, definitely you can get the perfect the cells. And it means what whole layer, whatever you have initially, that got split into small sub layers which are in this form. So to explain this, we take the help of the perturbation method. Happily, one can explain that. So for what value of the Rayleigh number, so we can get this instability. But here is you can see what is the bottom plate. Bottom is a rigid one, and top one is connected to the egg, right? So boundary condition is very important, right? I think Christian will know that aware of the problem of if it is one of the boundary conditions is rigid, then how much time, how much struggle one has taken. This is very simple. It is within 2 minutes you will get this type of pattern. But mathematically, if you want to trace out to understand the formation of the patterns, so he was spent more than 3 minutes, I think, right? So it is like that. Mathematically, it is challenging to understand, to explain the occurrence of such type of pattern formations. So this type of patterns occurs in nature, of course, in nature. So and then this hexagonal sense, if the boundaries or perfect conductors, okay, we can get it. You can see here, the interesting thing is the bottom is perfect thermally conducting, and side walls also here is thermally conducting. Okay, it means what side walls also showing some effect on this occurrence of this. Normally, what they take that bottom wall and top wall, but side walls they put as insulators. So they want to understand perfectly how the heat transfer propagation taking place. But here is this is ad hoc one. You see, that is it is like a cylindrical structure, but heating from below, and then just they try to see that whether we get the patterns or not. So I also get every day. I try to cook the milk and I get the patterns. Okay, because if I make improper things, then we can get. Okay, to understand such type of configurations, one has to use the perturbation methods, right? And of course, this is a small example I'm giving here is these are the Navier-Stokes equation, for example, equation of continuity and Navier-Stokes equation and the heat equation in perturbed form. And by taking the fluid is incompressibility and taking the help of this that is the gravitational effect, right? The buoyancy effect as a body force. So then if you use the suitable scalings, the scaling is very, very important. And if you use the suitable scalings, then accordingly what happens we can get we can get such type of the non-dimensional equations, and one can solve this type of equation using the perturbation methods, right, like regular perturbation methods. And here is you can see that epsilon is normalized with the help of the real number and with the help of the critical real number and the boundary conditions. So everything is perturbed equations, the equation of continuity, perturbed equation in 2D or 3D, what are the case, and this is Navier-Stokes equation, and in which a Prandtl number is there, and this R is known as Rayleigh number, and of course it is vector equation, and this is the heat equation, heat convection equation. I don't want to tell that what are the terms coming here, but my interest is that where we can apply the perturbation methods effectively to get the solutions, right? So I'll go to the next one, right? Okay. So then, of course, with the help of the perturbation methods, Krishnendu successfully got some. That is, I think you are also doing like energy method, right? So one can get such type of equations, right? It is known as Landau-Ginzburg equations, and that will help to understand the kinetic nature of the flows. Because initial stage means what? As I told you, that is conduction state we get, later convection. But at the convection state, what type of flow behavior will be? Whether it is kinetic behavior or whether it is weak turbulence, etc. Those things one can trace out with the help of this equation. It is called as Asymptotic equation. It was derived in 1969 by Newell and Wedgate, and Siegel also he also derived in the same year with the help of the regular perturbation methods, right? So like that, very highly challenging models one can trace it with the help of these perturbation methods. And let us see. That is, I don't want to tell that is why these scalings and etc. Of course, these are some of the numerical methods used, and then these plotted graphs. Of course, Professor Rani, he was published a paper in geophysical astrophysical dynamics. Is she able to trace out that taken the real numbers like this one, and this patterns she got it, but these are not regular patterns, right? So this is what is the value of critical real number when the boundaries are rigid? 1707, but it is not 1707. Number is 800. So we can say that is the flow is there, but it is subcritical flow we can call. Okay, so using, of course, these are all done by using some DNS methods, and she able to get it. And you can see that if it is more than that is 1707, it means for 3475, and Nusselt number is 1.052, and you can see that is regular patterns are there. So rules, and this explanation for the occurrence of this explanation, so she has used that is software, after DNS software, and with the help of workstation, of course. Of course, she can apply patent for this type of pattern. Of course, this is obtained for the Mandel convection problem, and taking Chandrasekhar number is 2000, and Rayleigh number is 30,139, very large Rayleigh number, right? And then taken the fluid is liquid gallium, and she able to get this type of pattern formations. You see that how it is three-dimensional patterns. Of course, it is not easy. 3D is very bad. So 2D only we fight with that, but 3D is very bad. So okay. So this things that is you can see this type of things we cannot trace with the help of your perturbation problem, methods, because due to complexity of 1D is okay, we can tolerate, and 2D okay somehow, like extend the 4 years, 5 years, okay, one can do the 4 problems like, but such type of things using perturbation means it is really very, very tough job. perturbation method has limitations due to the complexity of the geometry. Okay, so this type of problems we can use only DNS. Let us see. That is what happens in the case of the perturbation problems. Okay. Okay. So then when you have this type of equations, right? Equations like this, perturbable equations. Then in such case, firstly, what we do that we try to expand. That is dependent variable. U is what is here is dependent variable, right? And x is what it is say independent variable. It means you can differentiate with respect to x and so on. And then suppose if the equation includes the parameter like epsilon small one, so then we try to expand with respect to the epsilon as a power series, right? Epsilon of your choice. So as you know that a power series is converges. When it is converges, because power series is based on your epsilon, right? Epsilon square cube and epsilon power 4 like that you are having. So when a power series converges, can you tell me if epsilon is small? If epsilon is small, so then okay, the series is can converge. So the same small idea we try to put it and try to expand this is as a power series by taking epsilon is small. In your case, what epsilon parameter is very small, and physically also, if you observe any physical experiment in which the disturbance is very small. Suppose that if I curse you, then the small disturbance may grow in you. Suppose if it is large, then the problem comes, right? So let us see. This is the expansion we are having, and then in this we have the classifications. What is epsilon here? Epsilon is a perturbed parameter. Epsilon is what? Perturbed parameter. Suppose if epsilon is vanishes, epsilon 0, so then what happens? U is nothing but U naught. Is it not? So in such case, what are the perturbed differential equation you are having, right? That is become as unperturbed equation when epsilon is 0, right? So that is what we are having this idea here. And in this expansion, what is the first term we call? What are the next terms we call? So first term we call as this leading order term. Keep in mind that it has some name known as leading order terms. Okay, it means what? You see, if you see the Taylor series expansion f of x naught plus h. So how to write this is Taylor series for the f of say x naught plus h is small, So then f of x naught you having plus h f dash x naught is there plus say order of say h square. Can I say this is right? So in which the first term is the dominant term, and if h is small, then okay, this impact will be little bit on this term. And if you go higher order, so this impact on these terms may be very small on these terms, first two terms, right? So in such case, what we call this first term, we call as leading order term. Next terms we call as the correction terms. In Taylor series, from Taylor series, that is we can understand the same thing idea we put it here, and here is we having this U naught x is one leading order term. Other rest terms are there, epsilon u1, epsilon square u2. So they are the higher terms which we call as the correction terms. So these are the terminology you have to keep. Small ingredients are required to understand the perturbation problems, which are very, very limited. So this is one of the important things, right? So if the method is successful, so then u naught x will be the solution of the unperturbable equation. Okay, when it's successful, then u naught is what? It is called as the solution to the unperturbable. Unperturbable means epsilon 0. Right. So this is one of the algebraic equation. Let us take this algebraic equation is the u value. Okay, and u is equal to 1 plus epsilon u cube, right? And this is not a differential equation. Be careful. It is just some algebraic equation in which epsilon is included. What is epsilon here? Epsilon is very small. Now, how to solve this type of algebraic equation? You have your usual methods. What you learned elementary levels. Use the same trick to get the solution. Otherwise, another scope is just very simply you can solve using your perturbation methods. Let us see here the expansion. So you try to, as we have committed that you have to expand your variables with respect to epsilon. So let us see, this is expansion in which u naught is there taken as 1 for our convenience. Okay, you can see here if epsilon is 0 here, suppose epsilon 0, then what is u? 1. So that is how u naught is I have taken is 1. Okay, right. So this is the first one is what unperturbed. As I told you before that if yes. So here is what u naught is what solution for the unperturbed solution. Where is u naught is coming in the expansion first, right? So similarly, so same trick I am applying here. If epsilon 0, what is u naught here 1. So here is instead of u naught I have taken as 1, and rest of the terms are taken here. Okay. So what is next job? We have to submit this expansion to your equation. This is the same idea for the differential equations as well also for the algebraic equation. Same idea that we have that. Suppose that if you submit into this, submit into that, left side is also right side, and then try to collecting the like powers of epsilon on both sides, and you have this type of equation. And then how to get the solution? Because left side we having epsilon, epsilon square, epsilon cube, and dot dot we having infinitely many terms are there, but right side is what? Simply 0. Then how to proceed? A plus B plus C equal to 0, for example. What is that? A plus B plus C equal to 0. What is one of the solution? Previous solution we can take. A is 0, B is 0, C is 0. Right. So that's using the same thing. That is now equating the like powers of epsilon to 0. Right. Then what happens? We get the system of equations which are the homogeneous equation we can tell. Right. And non-homogeneous, it is sequence of the equations. Sequence of the equation we have. And then from the first one, simply you can get u1 value. Okay. From the second one, u2, because you know the u1, submit in this and you get u2. And then here is u2, you know, submit here, you get u3. Right. It means what? You are getting the solutions very simply. But now solving this equation, u is equal to 1 plus epsilon u cube, third degree polynomial equation. X square plus x plus 1 equal to 0, quadratic. You can write the solution what I told you. Then higher order, cubic, and fourth order, how to find these roots? It is not easy task. Okay, why not use perturbation method simply, and we can get it. Okay, now we have this is the way we have sequence, and then you see from the first one is what? u1 is equal to 1 we having, the u1 is 1 we got, and the solution of u2 plus 3 u1 is given by u2, this is equal to 3 we got because u1 we know previously, and the solution of u3, so you can find it using this is 2. So then submit into the expansion. What is the expansion you have now? Yes, here you have the expansion. In this expansion, u1 you know that, and u2 you know, u3 you know, and if you submit here, so finally you are here. U is equal to 1 plus epsilon and 3 epsilon square and so on. Okay, whether this works or not, that is important thing, right? Okay, so let us see. Epsilon is 0.1 if you take, and then you having the exact methodology. It means what? Just if you go to the system and solve it, like MATLAB and Maple, and if you solve it, then you have this is the solution for epsilon value 0.1. And if you use perturbation, this is expansion. If you submit 0.1 here, then you get the solution 1.142. It is close, right? And suppose if epsilon is again still small, 0.01, right? So in that case, so this is what the exact value, but you can see this approximate value. It is tallied up to how many digits here? 3, 4, 5, 6 digits is tallied. If you take epsilon value small, then it is the method is work that is better. Still small one if you take, so this is almost same. It means what? What is the conclusion from this one? Yes. So the perturbation method, as we have said that the perturbation method works if epsilon is small, right? Successfully it can give the good results, right? So in this way you can proceed. In this way you can proceed for solving this algebraic equation, right? So I hope you understood this, right? Okay. So let us take another. This of course this model is comes under regular or singular perturbation problem. A singular. Right. It is singular one, and then we go to the even though for that it is better it worked. Okay. Sometimes it is not. Okay, let us take another model. So it is regular perturbation problem. Let us take this, and then as usual, our expansions. Let us take x is expanded in form series of epsilon as can I say asymptotic or not? This expansion asymptotic or not? It is ad hoc basis we had it. Okay, if you take like this, you will get. Huh? Okay, 10 minutes. Little bit. So you want a break? Coffee break?